Okay, so we will move on to the derivation what we have done last class. So, we looked at in previous classes the ionization, the effect of ionization, how do we calculate the fraction ionized in a gas medium, and then if you use a diatomic gas, molecular gas, how the dissociation can influence the ionization process, because then you will have another endothermic reaction which is actually happening. It should happen to supply the electrons and ions. Okay, so by dissociation and then ionization, and how the ionization fraction and dissociation change as a function of temperature. And then we derived an important equation which we will also see in this class as well, to calculate the electrical conductivity or electrical resistivity of an arc. Okay, this is very important derivation because the heat generation is determined by the resistance to the motion of the charge carriers, isn't it? So, more the resistance, so obviously high heat, isn't it? It is like in a normal conductor. Okay, so if your resistance is high, so obviously you collide or you dissipate more energy because of the mutual collisions will be much higher, isn't it? So, we looked at the first equation to begin with is to balance the electrical charge, okay, of an arc, isn't it? The total electrical current of an arc, if you see that, so what do we do it? The electrical current of an arc is nothing but the ionic current and then electron current, isn't it? So, electrons would travel from the cathode to anode, the ions will travel from anode to cathode. Okay. If you provide resistance to this path, obviously that means that they are colliding to each other and they will drift after the collision, and if they are completely stopped, obviously that means that the entire energy will be dissipated there itself, isn't it? That means that the resistance is so high, you will end up producing enormous amount of energy at that spot. So, by knowing how difficult the path of the electrons and ions, then we can also calculate what is the resistance of the arc, that determines the heat generation in principle, isn't it? So, the deriving the electrical resistivity or electrical conductivity of an arc is extremely important, because from that we can also calculate the heat generation, isn't it? So, how do you calculate the heat generated in a simple conductor? What is the formula? I square R, isn't it? So, once you know the resistance of a conductor, obviously you can generate how much, you can calculate how much heat is generated. Okay. In other words, in this case we are going to calculate the resistivity of an arc, because that determines again how difficult the path of electrons ions in the arc. More difficult to the path, obviously then the collision will be higher, isn't it? Then what is the result of that? Then the heat generation will also be higher, isn't it? So, that's why this equation is extremely important, and we will use this derivation in various welding perspectives. So, for example, if you want to calculate the efficiency, what is efficiency again? How much amount of arc energy is transferred to the workpiece? Again, if you want to know the efficiency, then you need to know how much energy is actually generated, isn't it, in the arc. So, then only you can calculate the efficiency of the process. So, we always use, when you are doing heat input calculations, we use the efficiency, but then efficiency should be calculated from these fundamental derivations. Okay. So, it is very simple derivation what I showed you, how to calculate the electrical conductivity. So, what we have done, we just balanced the flow of ions and currents. So, if you add together, obviously that is the electric current of an arc. So, now we can calculate individually Ji and Je. Okay. Ji, it is ampere per square meter, right, per square meter area. So, it is nothing but what you have done, the charge of an electron and then number density of electron. Okay. Again, number density of electrons, how do you calculate? How do you calculate number density of electrons? From? No, from the Saga equation. Okay. So, Saga equation will give you the fraction ionized, right, isn't it? So, fraction ionized, what is that? Amount of electrons you generate or ions you generate, 1 minus electrons, isn't it? So, Ne we can be calculated from the Saga equation. and then if we multiply it with the drift velocity, average drift velocity is extremely important, does not matter whether it goes this side or this side after a collision. So, the average is very important. Okay. So, average drift velocity, if you multiply it with number density times the charge of electron, so that is the total ionic current, total electron current, sorry, is not it? So, now from this equation you can see that if the drift velocity is higher, that means that the collisions are lower. See, if velocity is higher, obviously current density will be higher, the electrons can easily move. So, then obviously you can also correlate the current generation will be lower, is not it? So, if a drift velocity is higher, that means that electrons are colliding to each other, okay, or there will be a close to perfect collision in such a way that drift velocity upon collision is decreasing. That means that the energy generation will be much higher, is not it? So, that is the simple logic of this equation. So, when you say the drift velocity, again drift velocity can be calculated between the acceleration times the time between two collisions, is not it? So, that is what, if acceleration is higher obviously, so then the time between collision will also be higher or lower. If it is accelerating much faster, that means that it is not colliding frequently, is not it? So, suppose if you want to calculate the average drift velocity, we need to multiply it with acceleration, okay, times time between the collision, is not it? Is not it? So, this is meter per second square times second will be meter per second, that is the drift velocity. But acceleration, how do you calculate acceleration? So, we will have to transfer this equation into the quantifiable entities. You cannot calculate the acceleration of the electrons or ions in arc medium, is not it? Similarly, the time between collision also is very difficult to find it out. So, we can convert that into more quantifiable variables. Okay, that is the purpose of transferring these two terms into the energy, the electric field and the thermal velocities and the mean free path, that can be calculated from the basic equations, is not it? Right. So, now then we replaced the acceleration. So, how do we replace the acceleration? Very simple. So, equation is F equal to ma, is not it? Right, and F is nothing but, so that is the electric field you apply, is not it? The electric field you apply times the charge, the elementary charge of an electron. Okay, so, then this must be equal to the mass of an electron times the acceleration of electron, the acceleration of the electron. So, now we can replace the acceleration of electron into by m, is not it? Yes. So, this equation we can replace the acceleration into the energy terms and mass terms, which are quantifiable, because you apply, E is the one you apply, the electric field in the circuit, mass of an electron, it is known entity, is not it? So, now similarly we also derived another relationship for time between two collisions, and time between two collisions, how do you derive, is the mean free path of an electron. Okay, so that is the average mean free path of an electron for a given temperature, you can calculate that, is not it, divided by thermal velocity, the average thermal velocity, right. So, average thermal velocity, that is the time between collisions, sorry, right. So, now you have relationship between seconds, meter per second, meter cancels out, you have second. So, that is your time between two collisions. So, now we can calculate the drift velocity, is nothing but you have E divided by me, is not it, and then time between two collision is nothing but Le divided by Ve. Yes, it is simple, right. Okay, now we have a relationship for Ve, that is what I asked you to derive in the last class, the average thermal velocity of an electron is a function of temperature. Very simple relationship. Okay, so that is luckily all the fundamental physicists from early 20th century they derived for us, isn't it? Okay, we should be thankful for them. So V is nothing but thermal velocity is 8 Boltzmann by pi, isn't it? So now we can replace V with this equation. So now what will happen is E LE and then ME times square root of 8 kT divided by ME pi. So ME goes inside into M square, ME square, right, and ME cancels out, and then UE becomes divided by 8 ME kT divided by pi. Yes, it's clear. So now we have the equation for drift velocity of an electron, right, under a electric field, right. So now if you use this to UE in this equation, now we have the electric current density by electrons, isn't it? So that will be so E times there is already another E, right. So it becomes E square Ne, number density of electron, okay, and then your applied electric field, and then Le, isn't it, divided by square root of 8 Me kT by pi. It's clear? Yes or no? Okay, so now we have the relationship for the electron current density. So the ampere per square meter. Similarly, the same thing can also be derived for ion, isn't it? And everything is the same. The same thing can be derived for ion as well. So again the electron charge, number density of ion, the applied electric field, mean free path of ion divided by square root of 8 mass of an ion kT by pi. Everything is same. It is also fundamental particle. It is a charged particle, right? Isn't it? The same derivation can also be derived for the ion density as well, isn't it? Because the same charge carriers, the velocity, thermal velocity of a particle, it is the same as an electron. And if you look at these two equations, okay, the electron density or ionic density is fully determined by temperature, isn't it? Because the Ne and the Ni, when the ionization is happening, it is the same, isn't it? Number density of electrons and ions, E is the same, okay. Mean free path is more or less the same at a given temperature, okay. So the important factors that determine the field, the electric current in the arc is temperature. The other important thing is here, if you divide Ji by Je, so assuming that mean free path is the same, and this will become isn't it? Yes or no? Yes? So if you divide Ja by Je, because all of them are almost same, assuming that mean free path is the same, Ja by Je equals to square root of Me by Mi. So So, now we all know the Me is much less than Mi, because the mass of ion is an atom, close to an atom. Electrons compared to the ionic mass is negligible, isn't it? So, if that is the case, then J must also be much bigger than the ionic current, isn't it? According to this relationship what we derived, isn't it? It's clear? So, we derived the electron density and ionic density in an arc. The current density is inversely proportional to the mass, square root of the mass. So, if you divide JA by JE, obviously it must be equal to square root of ME by MI. We know that the mass of an electron is much less than the mass of an ion. Therefore, according to this relationship, Ji, the electron current, must be much greater than the ionic current of an arc, isn't it? So, that means that the entire current flow in arc is determined by only the electron current, right. So, that means that the entire heat generation is determined by the flow of electrons, isn't it? So, we can safely neglect the ionic part. So, when you are doing calculations, because the mass of an electron is much tiny compared to the atom's mass, you are comparing elephants and a small orange, isn't it? So, if you look at this relationship, the entire current flow in arc is determined by the flow of electrons, right. So, we can safely neglect, because of the mass effect, the ionic density can be safely neglected, right. So, now we can derive, we can safely say that the electrical conductivity is, how do you calculate the electrical conductivity from the electron density, is nothing but, suppose if you want to calculate the electrical conductivity sigma, is nothing but the electron density divided by the total electric field. Okay. That means that Je divided by E. So, that is the conductivity, right. Conductivity is nothing but Je, that is electron density in an arc, because Ji, the ionic density, can be neglected because of the mass effect. Okay. So, you can do the calculation, but it will be 10 power minus few fractions, few hundred, according to this equation. Okay. So, the electrical conductivity of an arc is nothing but Je divided by E. So, this equation, if you divide by E, then E goes away, then this becomes sigma. So, that is the electrical conductivity of an arc. 1 by sigma is electrical resistivity. So, if you do reciprocate this equation, then it becomes electrical resistivity. Wow, happy. Now, we have R. We can calculate now. Okay. If you know the resistivity, obviously we can also calculate the resistance. If you know resistance, obviously we can calculate the voltage, isn't it? If you know E, and if you know voltage and current, you can calculate heat, isn't it? That is what. So, this is how we calculate the heat generated in the arc. It is clear, isn't it? Okay, good. We look at the slide again. If you have any questions, please let me know. Right? It's clear. So, we will just quickly look at the derivation again. So, electrical conductivity of an arc, how do you derive that sigma? So, electrical current is, we can assume that it is a total current, the electron current plus the ionic current. Electron would travel from cathode to anode and the ion would travel from anode to cathode. So, now we are deriving the equation for the electron current and an ion current. The electron current is nothing but E times the number density and then drift velocity. Number density can be calculated from Saga equation, because that gives the amount number of electrons percent, isn't it, as a function of temperature. And drift velocity we do not know. So, we will have to derive an expression for drift velocity. Okay, drift velocity is nothing but acceleration times the time between two collisions, isn't it? Acceleration again we do not know. So, we will have to find some expression for that. F equal to ma. F is here is the electric field you apply. Okay, so, that is times E, the electric charge, that gives the force, isn't it? And force equal to ma. So, ma is nothing but force divided by mass, that is what here. Okay, the time between two collisions. So, we do not know time between two collisions as well, right. So, that can be converted into mean free path divided by thermal velocity, right. So, mean free path is Le by thermal velocity, and that is the expression for the average drift velocity. So, once you know the drift velocity, and we also know that the thermal velocity is square root of 8 kT by me pi, that is the average thermal velocity. So, now we have the predictable means of the expressions. Okay, so, we already converted all the variables into the predictable variables. So, now if you can replace the drift thermal velocity into the square root of 8 kT by me pi, then we have the expression for the average drift velocity. So, nothing but E times the field, the mean free path of an electron divided by square root of 8 me kT by pi. So, now the electron current is E times Ne times drift velocity, isn't it. So, you replace UE with this expression, you will get the expression for the electron current in an arc. Okay, this is very simple derivation. Okay, it is not even +2 physics. Good. So, similarly, we also derived for ion. We replace Ne with Ni, number density of ions. Okay, then the mean free path of ions, mass of an ion. Okay. So, assuming that the mean free path of ion and electron is the same. Okay, so, if you divide Je by Ji, so obviously it becomes square root of Mi by Me, or other way around, does not matter, right. So, that is a basic expression understanding we can have from this derivation. The understanding what we have is, if we divide these two, obviously Mi, the ion mass, is much higher than electron mass. Okay. So, because it is an ion is one electron less than an atom, okay, whereas an electron is nothing compared to an atom. So, the mass of an ion is much higher than the electron mass. So, obviously, according to this derivation, if this is the case, okay, the electron current will be much higher than the ionic current. So, even if you use the total electric current Je plus Ji, okay, and this is negligible, could be 10 power minus 23 or so, there is no point in using that. Okay. So, the entire current is determined by the Je, okay, the electron current. So, therefore, we always assume safely when you are doing the calculations for heat generation, the ionic part is neglected. So, we always use the electric current part, the electrons determine the heat generation, that is rate controlling. Okay, it is good. So, we can always safely say that the electron current makes up the majority of arc current. We can neglect safely the ion current. Okay. So, once we know the expression now, the conductivity is current density, the total current density, where we can even still keep Je plus Ji, but again Ji is negligible, we can take it out, by the field strength E. So, that is what conductivity of an arc. Okay. So, if that is the case, the electrical conductivity of an arc, so we give the expression for Je, the E goes out in Je, and this is the expression to calculate the electrical conductivity of an arc, and 1 by sigma is resistivity, right. That is it. So, now we can do the welding, right. So, we safely calculate the heat. Okay. So, now we can ignite the arc and then we can calculate. But then there is one more trick before going to the welding process. Now we have the heat generation, but that is transferred through conduction, convection, radiation, right. But now we need to understand whether all the heat we generate, it is effectively transferred. Okay. So, then it is 100% efficient process, but it is never the case. Unfortunately, in most of the cases we lose whatever heat you generate by this equation. Okay, it is not transferred properly. So, now we need to have a balance. Suppose if you calculate the arc energy, okay, so that is U conduction, radiation, U convection, right. That is what we saw in previous class. This we can calculate here, but then how much is transferred by conduction, convection, radiation. So, that determines the efficiency of the process. Okay. So, now we will see in subsequent slides how the conduction, convection, radiation happens in the arc. Okay. So, then in subsequently when you look at in each process, the conduction, convection, radiation can be different. For example, in submerged arc welding, we completely shield the arc by flux. That means the radiation heat loss is almost negligible. Okay. In some processes, we also melt this consumable and deposit to the base material, like in GMAW process. That means that heat required to melt the consumable, it is again transferred to the workpiece. Whereas in a non-consumable welding process like GTAW, gas junction arc welding, whatever heat is used to heat the consumable or the electrode, it is not transferred, it is getting wasted, is not it? That means that efficiency goes down. So, each process based on its characteristics, the efficiency change. Okay. So, we will see one by one when you are looking at the process how we can use this equation to calculate the efficiency of the process. Okay. So, if you look at the electrical conductivity, and we can calculate using this equation very beautifully. For example, this curve shows the electrical conductivity of an argon as a function of temperature. Okay. So, obviously, at lower temperature you are still ionizing, is not it. So, the ionization is still continuing, and upon increasing temperature the ionization saturates. That means that Ne saturates, is not it, upon increasing temperature sufficiently. So, obviously the conductivity increases. So, once the temperature increases sufficiently, if Ne becomes saturated, so then conductivity approaches at a constant value, right. It is clear, is not it. So, Ne is a function of temperature, Saga equation, and temperature determines Ne from Saga equation, right. So, once you know that, we can calculate the conductivity, and if you reciprocate, it becomes resistivity, is not it? So, once you know resistivity, obviously you can calculate resistance, and then I equal to, again I is nothing but your E, the field strength. What is left is V, we can calculate, and then the entire heat generation is nothing but V by I, sorry, V times I. So, now we have an expression to calculate the electrical resistivity of an arc. Yes, it's clear? Good, from the fundamental physics.